9 years in the US, 7 in Boston on the East Coast, and then 2 in Berkeley on the West Coast. I went to US to do experiments in quantum computing, actually. And then after my first year, I found myself searching for dark matter. So we can talk more about it after I finish my 5 or 6 slides. It's common, right, to start walking from one point when you're doing science, when you are questioning things, when you're learning about, especially in experiments, when you're learning about how to build a setup, right? You start from one point and then you find yourself somewhere else. It happens, right? And more than often, the systems that you use, for instance, for quantum computing, the quantum sensors, are applicable, are usable in other fields, such as dark matter searches, right? So I do not want to promote experimental physics over theoretical physics, but I'm biased. I'm an experimental physicist. So I should say, good thing, the exciting, the fun thing about doing experimental physics is that once you learn how to do something, you can do something else using similar techniques, right? The difficult thing is doing actually that something, the first thing, because more than often the experiments do not work, right? You start, you press the button, it doesn't work. And if it works in the first press of the button, you get skeptical. You think, ah, something went wrong, why does it work? It shouldn't work on the first hit, you know? And then you panic, and then turns out something was missing, blah, blah, blah. Right, so it takes about a year or so in my field in atomic molecular optical experiments to make something work, to get meaningful results, 2 or 3 more years. I do not say this to scare off any potential master's students here, but things take a while and you have to be determined, you have to be in the lab, you know, to make things work, you have to tinker things. But the fun thing is, in the end, something works. If something works, you feel very happy, right? And then it starts to be you start getting addicted to that feeling, I guess. Somehow, like how people who drive cars fast, like driving cars fast, becomes an addictive thing. So I guess experimental physics is sort of like driving a Ferrari. If I have to, you know, explain it very broadly. All right, good. So you do search for dark matters, although since now I am a faculty of my own, that will not be my sole focus, right? I will not only search for dark matter, but I will build devices that could search for dark matter, that will search for dark matter, but I will use those devices for other purposes too, which I will explain for a little bit. Good, so I titled it Opposite Attract. Opposites attract, which is a common saying. People see bar magnets that attract each other. If the North Pole and the South Pole are close, they attract each other. People then like to generalize things into human lives, as if the opposite personalities, they also attract. So that became a common saying. But I will explain why we measure magnetic fields anyways, right? Why do we care? Why do I care about magnetic fields so much? Good. Since yesterday was the 100th anniversary for our republic, which I am very proud of, and I'm very happy to be back here, I just wanted you to remember one thing that Atatürk said, and I really like this. He said we only need one thing to be hardworking. Tek bir şeye ihtiyacımız var, çalışkan olmak. And it's as we say in Turkish, ear into my ear. It's kulağınıza küpe olması gereken bir laf, right? What we have to do, what we have to be is hardworking. And the person who loves their country most is the one that does their job best. Good, okay, with that. Magnets, what are magnets? So I personally, apart from physics, I like etymology a lot. When I hear a new word, especially since most of scientific words in physics is derived from Latin, right? It doesn't come naturally to us. as it does to English-speaking people. So when you hear magnet, I kind of say, okay, fine, you say this is a magnet. Where does it come from? More than usual, whenever you hear a new term, if an English speaker hears it, they have a natural instinct towards what it could mean. For us, it's different, right? For us, it's we have to sort of first get used to that word. So anyways, I usually go on and look up how the words came about, you know, the root, the etymology for any of the terms that I come across. Magnet was very surprising. Turns out, magnates are, you can see a coin there, they're fighting Greek, a group of Greeks in ancient Greek that were fighting, you know, that were on horses and all. They moved to the ancient Greek city of Magnesium in Meander, which we now call Manisa on the Menderes River, right? And lodestones, you see a stone that attracts lead, cheated nails. Thank you very much. Good. So these are lodestones, and magnetite stones are not found too often in nature, naturally, and lodestones are very special in that sense. And it is thought that the word magnet comes from this area of Manisa, where magnetes were in. And so these stones are from Magnesia or Manisa, right? And the thing that we call magnetism, like the way that it is usually shown, the way that magnets are usually shown, is by a two-polar, right, north and south pole. In a bar, you have north and south poles. That's how people usually show in introductory physics courses the structure of a magnet, which is completely untrue. Right? We do not have a distinct, a very clear green and red areas where, you know, it is south and it is north. That is not true, right? What is true is the fields, right? We have magnetic fields that are generated, that are created due to small poles inside a large magnet, right? And these magnetic fields, here as you see, have closed loops. The whole idea of magnetism is that magnetic fields form closed loops, right? This is all you have to know. And when you have a closed loop, it is natural, when you have a direction that goes through, it is natural to think that, there must be a north and a south pole, but this is not the truth. And why do magnets attract? So now I'll answer my question from the beginning, right? Why do opposites attract? It is to decrease the energy that is stored in this system. For instance, if you have two magnetic fields around a magnet, a ferromagnet, whatever it is, because you have closed loops, right? You will start having closed loops in this from one of the magnets to the other two, right? And you want to decrease this energy, right? You want to close this loop, right? And therefore, these two magnets pull each other, right? It is not because they have two poles. It is to decrease the energy stored in the system. Now, I do not like drawing magnets horizontally. I like them vertically because I work on spins and usually draw spins vertically. So here I flipped it 90 degrees. And similar to this idea of a bar magnet having closed magnetic field loops, a spin, right, the smallest rotating entity, because it rotates, creates a magnetic field, right? With the right hand notation you see, with my right hand I define the magnetic field direction. So if this, as you see the ball, if this rotates clockwise, it creates a magnetic field upwards. If it rotates counterclockwise, it creates a magnetic field downwards, right? So, so this is actually, what I told you about is a dispute between the magnetic pole model, which is not the truth actually, and this is a dispute between the magnetic pole model and Amperian model, right? What I told you about the loop, the magnetic field loops, is the Amperian model. All right. Anybody has any questions? Good. All right. So magnetic fields, I said, I already introduced the term, right? The magnetic fields. What is a magnetic field? It, right? When you have a closed loop, it is the field, how much this magnet, how much the magnet's effect is felt at a certain point is magnetic field. At Earth, in the center, we have a core, right? The Earth is a core, which is not like the like the core of a of any fruit that you know, like avocado. So avocado has green exterior and a large core interior. It is not like that, right? It's not a solid core. It's fluid. It's flowing, right? Because of very high temperatures. So the common picture in people's mind is that this core is magnetic, but it is not. This core is at, I think, around 700 kelvins, which is really, really high temperatures, and it's higher than a Curie temperature, named from Marie Curie, right? 2 times Nobel winner. And she said that if you have a ferromagnet and you heat it up to real high temperatures, then it no longer is magnetic. Right? It loses its magnetic properties. That's what happens at the Earth's core. But instead, what happens with the Earth's magnetic field is that because of the flow, because there is motion, right? Because there is rotation, a magnetic field from the center of the Earth is generated. And the magnetic field lines that we see, right, in this picture, and the magnetic field that we measure on the surface of the Earth is due to that. As you can see, the field value that you would measure on the equator there or the North Pole there would be different, right? This is not like gravity in that sense. It is not homogeneous, more or less, so to say, around the Earth's surface. And also, you sometimes hear that Earth's magnetic field flips, right? And I personally, when I heard it in high school, I felt this internalized panic that, oh no, something flips. Oh, as if I don't have enough problems. Now the Earth's magnetic field is going to flip. What will it do? The same sort of panic that was felt in the public when CERN first started its run, and they said, a black hole will form. What will we do? It didn't form, and nothing. As far as we know, no big problem arises when Earth's magnetic field flips, which it does in about 300,000 years, once in a 300,000 years time, right? And somehow it flips, and the reason, the method that we think, the way that this happens is that the rotation of the fluid inside the Earth, changes, right? The fluid starts. It is not very highly, how do you say? It is not very homogeneous. It's not the time evolution is not very, straightforward. It's not very oscillatory, so to say. It somehow sometimes flips, right? And then the Earth's magnetic field changes direction. That is the idea, and it is also very common to draw Earth like this, which is not true, but it is still very common. And how auroras happen on the north and south poles is the interaction of this Earth's magnetic field with the charged particles on the atmosphere, right? And the reason that this happens on north and south poles is that the Earth's magnetic field is mostly felt in the ends, in the pole ends, of the Earth. Good. And I just wanted to show you the first magnetic that measured the Earth's magnetic field. This is by Gauss and Weber. Gauss actually found did this, would put this setup in his yard, in his garden. So it's a nice, beautiful garden. Although we had a garden, I doubt my husband would allow me to put a magnetometer there. He would say, you have a lab already. So, but Gauss did put it in his garden. And the idea was that he had a magnet, right? That a ferromagnet that he turned on and off its magnetism. So when it was not magnetic, it would just still stay there with hang on a golden chain. And when it was magnetized by a loop that runs current around it, when it was magnetized, it was pulling itself. It was aligning itself with the Earth's magnetic field. And looking at that alignment, he was measuring the magnetic field strength, right? So that was, I think, around maybe 1700. So Gauss, I think, lived in 1777, around that, if I'm not mistaken. Good. All right, so this is magnets. Now we're getting into more current science, let's say. Although nuclear magnetic resonance has been around since the 1960s, I think, it has its own Nobel Prize from either 70s or 80s. And what nuclear magnetic resonance means, it has nothing to do with nuclear power. You know, it doesn't divide nucleus into different parts, right? It has to do with nuclear spins. That's why it's called nuclear. And NMR devices, and later I'll tell you about MRI devices, magnetic resonance imaging. These devices use magnetometers to measure in each individual spin's magnetism to extract information on molecules, right? So this is quite a jump from 1700s to 1900s. But bear with me, this is one of the biggest achievements of magnetism. So NMR actually is one of the best ways to measure a magnetic field, right? What happens when you have a spin is that, as you guys all know, and as I have shown you the polar picture, a spin in an energy level, right? If a spin is put under a static magnetic field, A0, as is shown, I think maybe I have a laser here. No, it's not a strong laser, but I should have brought my own laser. Strong laser. Okay, good. So, well, I give up. Even I don't see. All right. So if I had a B0 field that is drawn there, right, an upward arrow. So my finger is the direction of the B0 field. Then the Zeeman splitting, a little thing we call a Zeeman splitting, splits the energy level of a spin that either points downwards or upwards. Any spin, right, that points upwards would have a smaller energy than a spin that points downwards. So in that sense, that picture is wrong. I made a mistake. I should have corrected it. And I remember making that mistake and thinking, oh, I will correct it. Of course. So the lower energy state, the energy state that you see below, the downwards energy state, should have been spin up. And the higher excited energy state should have been spin down, right? So spins, if there is magnetic field, want to align themselves with that magnetic field. In that sense, somehow like a compass needle, right? When you have a compass needle, it aligns itself with the magnetic field. So a spin, a very, very tiny and impossible to see with eye, a very conceptual even, not even a physically real compass needle, it aligns itself with the magnetic field. Now, more of the spins, the dots that you see, the circles that you see are the spins. They symbolize the spins. They tend to be in the lower energy state. And the idea is that the splitting equals to gamma B0. Gamma being pure magnetic ratio, which is specific for each atom. a carbon and hydrogen and a lead atom has different gammas. And that is the signature of each atom, and that's how chemists and doctors differentiate different atoms from each other using NMR. They differentiate gammas. They look at the splittings, the energy splittings, and they deduce the energy splittings, and then they realize, there must have been a hydrogen there and an oxygen making this bond with carbon. Okay? So that is the big idea, and we call this a frequency actually because the energy splitting ends up showing up as the spins moving up and down, right? And when the spins move up and down, we monitor their motions, or when the spins start flipping, right? We monitor their motions and measure that motion, and the frequency of that motion gives us a hint of gamma, of the splitting. And this motion happens at the energy splitting. If the splitting is more, the motion happens in a higher frequency than if the splitting is less, happens at a different frequency. So, good. So if the idea of NMR is that there is resonance, that if you're on top of a static magnetic field, B0, if you excite the spins with an oscillating magnetic field that oscillates at the same frequency of this energy splitting, then a resonance happens. If the omega-1 that you see cosine omega-1t, that means oscillation at cosine, right? Cosine oscillates. The oscillation frequency omega-1, if it multiplied by the Planck constant equals to gamma B0, then you have resonance, and you have this nice Lorentzian peak. So this is the peak of NMR. This is what NMR measures, Lorentzian. And never mind about the equation. The beautiful thing. So I'm an experimental physicist. I like quantum physics a lot. I use quantum physics daily. But the beautiful thing about NMR is that it can be explained classically. In the end, if you have a lot of spins, right? If you have a fluid, let's say of even a milliliter, you have a lot of spins. And if you have a lot of spins, this phenomenon becomes classical, right? And the magnetization, the magnetic field that is produced with the spins due to the spin motion can be picked up and can be measured and can be explained classically. You do not need a quantum device for it. If you have a quantum enhanced or a quantum sensor, then you would have less noise. That is the idea. But this is not you do not need a quantum device. You do not need a quantum computer to measure this. So right, and Bloch equations, the key word here is Bloch equations. Bloch equations describe the motion of the spins classically. So that's the beauty of this, and that's why it's already useful. It's found used since 60s, even though we didn't know the whole theory perfectly now. All right, then a little bit about magnetic resonance imaging. I've shown you the idea of magnetic resonance imaging. I've shown you an NMR, how NMR works, and I told you that there is a large static magnetic field, right? It is very important to have a large static magnetic field because Earth's magnetic field is also static. You need to go beyond that to excite the spins, to split the spins in a detectable way, in a detectable frequency, right? In a detectable Larmor frequency. I didn't define Larmor frequency by word, but it's gamma B0. Okay, so the Larmor frequency is how much each atom's spin's energy level splits due to a B0 field. So this is a magnet. This is a solenoid. You solved a lot of solenoid questions probably in your Physics 102 in high school. You know, what does a solenoid do? It's a loop that carries electrical current and generates a magnetic field. This is a loop of, I don't know, 100,000 turns. It's very difficult to make, right? Usually machines make these. During my PhD, we had this fantastic Russian postdoc. Postdoc is postdoc in scholar, someone who already has a PhD but doesn't have a permanent academic position, somehow in a limbo, you know, Dante's Inferno. I was a postdoc for 2 years before becoming an assistant professor. It's good. You know, you don't have to find funding for your own lab. You don't have to buy things for your own lab. You work in somebody else's lab, but you don't have independence. You know, there's a price for everything, I guess. But postdoc is part of academia. Not so much in Turkey. There are some postdoc positions, I guess, but it's starting out here recently. But anyway, so we had this fantastic Russian postdoc who sat down and wound a very uniform, a very beautiful looking loop on a core, on a what do you call this? A ring core, you know. He wound around the ring, and it took him maybe a week to wind 1,000 turns, but it was perfect. It looked like a machine made it. And we had good homogeneity with it, good homogeneous magnetic field. What a homogeneous magnetic field means is that around your central axis, when you measure magnetic field, you measure approximately the same value, right? It's not like Earth's magnetic field, right? It's not less here, more here. It's pretty homogeneous. So the big thing, right, in coil mounting and magnetic resonance imaging, MRI, is to have homogeneous coils, or rather coils that, even though if they have inhomogeneity, controllable inhomogeneity. You know the magnetic field inside, and that's very difficult, and that's a whole different field on its own. That's why magnetic resonance imaging devices, MRI devices, are expensive. They are not easy to make. And once you make them, you wind these coils. This is not a copper loop, this is a superconducting loop. What a superconductor is conduct super, right? It's superconductor. But it doesn't conduct super, it doesn't have zero resistance at room temperature. It has zero resistance at very low temperatures, below liquid helium temperatures, right? So helium is at room temperature gas. Below 4 Kelvin, it becomes liquid. And we liquidify the helium that is found on Earth. But the problem with helium is that it evaporates. Once it evaporates, it leaves the gravity, and it flies through the Earth, goes into space, and we lose helium. We have only finite reserve of helium in the Earth. And the problem with these superconductor-based solenoids is that they need to be cooled down to meaningfully work. But we have a limited amount of liquid helium. And they're expensive. Actually, a liquid helium, a bottle of liquid helium, or a liter of liquid helium, you buy in 80-liter tanks usually. You must have seen them outside UNAM and, you know, around the campus. There are big metallic bottles of 80 liters. It's as expensive as a good wine, right? It's an expensive thing to buy. Of 80 liters every other day, so this is a demon to feed, as most MRI people should agree with me. So the whole thing of measuring MRI, taking MRI scans becomes expensive because you have to supply liquid helium to it, you have to have a good coil that has homogeneous field inside, right? So this is difficult to have, but we have one. And here you see some gradient coils. On top of this very nice homogeneous magnetic field, you have gradient coils. And I'll tell you more in a second. So this is how an MRI device looks. Actually, it is called NMRI, nuclear magnetic resonance imaging, but so as to not scare patients with the word nuclear, they omitted it. They said, oh, no, not nuclear, but it is nuclear. But it's not, you know, it has nothing to do with nuclear fission or anything, right? There's no splitting or nothing. Don't worry. But anyways, so an MRI machine usually costs $2 million, so give or take. It weighs a lot, 7 tons, takes a lot of helium, liquid helium, LHE means liquid helium, and it creates a magnetic field of about a Tesla, which, as I said, so the Earth's magnetic field is about 50 microteslas, and it's much more than that, right? Produces a large magnetic field. So the gradient coils, the use of gradient coils in MRI is to create a gradient. If you enter an MRI machine, they create a magnetic gradient around your body. You see the gradient there. The B field is on y-axis. On the z-axis lies the body, as you see. The magnetic field that the feet feel is different than the magnetic field that the head feels, and on different parts of the head, the magnetic field that is felt is different. And that's a method, right? Not all MRI machines do this, but if you want to have sliced photograph, sliced imaging of your brain, you have a gradient field. The spins, the water spin, they measure hydrogen as far as I know. The water spins, the hydrogen spins that the molecules in your chin feel have a different magnetic field than the ones on top of your head, on the brain. And that results in a different frequency, a signal in a different frequency. And that's how, with a single machine, with a single pickup device, you can pick up different frequencies and then put them into an image. So this is picked up in real time with a single machine, right? With a single pickup device, a single coil, that is. So the bottom of the head and the top of the head with the nose and all. So this is brilliant. This is a beautiful way of doing this. This is very simple, right? To put things in gradient and to measure different parts, slices of the head at the same time. This is a brilliant way of thinking about this. And I personally find this beautiful thing. And this is, you see, we have horizontal, here we have horizontal images of the head. And again, you require resonance. This is still a resonance imaging. You still require resonance to be able to measure. What you do is you excite spins at V0 cosine omega 1t at different frequencies at the same time to pick up this. Good. Now, this MRI device is at 4 Kelvin, right? This device. You are not at 4 Kelvin. You would die actually. 4 Kelvin is minus 273 degrees Celsius. Very close to absolute zero temperature. When I was doing my PhD, we had our setup cooled down at that, and Boston was a very cold city in the winter. We had snow this high. It was horrible. The first winter I was there, Ankara is cold, right? So I thought I can handle it. This is nothing. The first winter I was there, I thought of coming back. Oh no, I can't do this. It snows this much. People build igloos. And the streets are full of snow, and the pavements were full of snow, and the Boston, as far as I know, the Boston Public Works doesn't have to open the pavements, but individual people, homeowners, have to, and they do not clear the whole pavement. They clear a tiny area that only a foot can make. Okay, only a foot can fit. So you have to walk like this. And if in the corridor that you're walking, if there's someone else on the other side of the pavement in the corridor, then you have to stop, and it's like two goats on a roof, and then you have to think, you should go, but I have to hurry. I'm also doing important things, I think. So you stop, and then you give them the road, and then the same thing happens. It's horrible. So anyway. It was a very cold city, and I was in the lab more than often after midnight, doing runs and, as we call them, cooling down our setup to 4 Kelvin. And already the city is cold, it's winter, the lab is cold because we have lasers. Lasers need to be temperature controlled, and usually is a slightly below room temperature that we kept inside. And so it's already a cold room, and then I have this cryostat. A cryostat is like it's basically a bucket that you fill with liquid helium, and then liquid helium starts evaporating from the bucket. So it cools down the area around too. It evaporates, but it is not at perfectly at room temperature. It's still cold. So the room gets colder and colder, and you're there running the experiment. So that was difficult times. I put on my winter coats while working, which is not very comfortable. But anyways, so I still like working with liquid helium. I prefer not to these days anymore, and I'll tell you more about it. I like doing magnetometry, magnetic field measuring at room temperature these days, to not to feel cold ever again. So anyway, this device, this MRI device, cools itself down. The tube inside, this is the crash that the MRI device has. It cools that down at 4 Kelvin, right? They put helium into that region, but the person where the human enters is not cooled down, it's at room temperature, so not to worry. But this device works at 4 Kelvin, which requires liquid helium, right? So something very exciting that not only me, but many others who do magnetic resonance and magnetometry, magnetic field measuring, that work on developing techniques, are excited about. What we are excited about is temperature MRI, maybe. So there are people, to take another break here, there are people who work on, so I told you that these are superconducting wires, right? There are people who work on higher temperature, above 4 Kelvin superconducting wires, and or superconductors, not wires yet. But most of the news that you hear in the news. If you follow physics news, you hear people talking about, they found a high temperature superconductor. One happened in August, I think, this year, LK99, I think, which turned out to be, as far as I know, a bogus. And most of those are, right? Anybody who comes at you, so don't fall for those. If anybody comes at you and says, I have a high temperature superconductor that works at room temperature, at 100 Kelvin, be skeptical, okay? Do not fall for them in the beginning. Think. It is very unusual for materials to have superconductivity at room temperature. So we do not expect that to happen anytime soon. It might happen in the end, one day, I do not know, but we do not expect that to happen anytime soon. And even with that, we do not expect to have a machinable, bendable wire out of a superconductor at room temperature, right? What we require is not only a superconductor, but a superconducting wire that is bendable, that is machinable. That is also a very special blend to have. Anyways, so to free MRI or to free NMR to free it from liquid helium, from cooling things down, we require either a room temperature superconductor, which probably won't happen anytime soon, or we have to think twice before using superconducting wires anyways. So this is not my work, but I find it very, very exciting too. Nevertheless, these people used permanent magnets. You know, the magnets that you have maybe in your pocket, maybe on your refrigerator, right? If you're like me, I have tons of magnets, which I know I'm thinking I should have bought a few. But anyways, so they put permanent magnets together in a cylinder, what we call in a whole bath cylinder. So magnets is a medium, I don't know how to pronounce that, sorry. So they put ND-FeE magnets and they align them, right, in very calculated ways to create a permanent, static, large magnetic field that is homogeneous in this direction. All right, and you do not need to cool this down. This magnet stays on. You do not need to run a current through it, right? You can put coils, gradient current coils that you can run currents through, even though it's copper. You might have some losses, some couplings, some technical issues with it, but you could still do it. And they did it, and they did some measurements with it. Not as good as the measurements that you saw before, with proper, cooled down MRI device. However, they took measurements, and I think this is beautiful that they had inductive sensing. They sense the brain, they measure it, but they have limited sensitivity, and this device is not modular, it's very heavy, it weighs 122 kilograms, not as heavy as an MRI machine, but still quite heavy. Right, and so this is very exciting. I do not work with permanent magnets. I do not work with a Hall-back cylinder, but still, this is I think a motion in the right direction. But we'll come to more on what I work on. Before that, I want to talk about magnetometers. I kept saying magnetometers. They are magnetic sensors, right? Magnetometers. The simplest magnetometer that you know, probably from classes, is a coil with a ferromagnetic core. What happens is that if there is magnetic field present, a current is induced, right? As Faraday tells us, a current is induced on the loop. Another simple magnetometer is a compass needle, right? A compass needle here. So these are my drawings. I hope they're clear and explanatory. I'm not there to do this. I think if I could learn how to use Photoshop, that would be great. But I do these in PowerPoint. I tried to do the spin dynamic thing was in MATLAB. I simulated that in MATLAB, and that was the highest point I ever reached in terms of graphics. But I hope one day I'll learn how to use vector graphics. Anyway, so this is a compass needle with so this is a ferromagnetic needle. The needle that you have in your compasses, in your pocket compasses, is a ferromagnetic needle. Is a tiny, very thin needle that aligns itself with the Earth's magnetic field, right here drawn in this axis. There are things called Hall probes that do measure magnetic field, static magnetic field. It is what it does. It's a slab. It's a conductor. It has some voltage across it, so it has charges, positive and negative charges on two ends, right? And if there is a magnetic field that flows through it, a current is formed in the direction orthogonal to the voltage. Hall probes measure static field to maybe sensitivity with a certainty of 50%, which I didn't know when I was trying to measure the static magnetic field to calibrate our first setup. It said, your static magnetic field. So we put it together a setup before investing into a big setup during my PhD. We made a small mock, setup that was similar in essence to what we wanted to make in a more expansive fashion. And we wanted to measure the magnetic field. And we said, let's use a Hall probe first to sense the magnetic field, then we will use NMR to measure the magnetic field. As I said, NMR is a very good method to use to measure the static magnetic field. So we put the Hall probe on top. We measured some magnetic field. We said, you have 0.1 Tesla. And we started looking for NMR around 1.1 Tesla, whatever frequency that corresponded to in our liquid sample. And we sat down and we tried to measure no signal, a month passes, no signal. The graduate student's nightmare, no signal. I doubted everything. I doubted that part, I resoldered things, I put things together again, I redid everything. That wire might have cracked, or the device might be broken, or the pickup device might be broken. I never doubted the Hall probe. Until 2 months passed, or maybe a month and a half or two, and I said, okay, this is it. I no longer can doubt what I did, right? I checked everything, I redid everything. Why don't I doubt this device? And turns out what it said was 0.1 Tesla was actually 0.15 Tesla. It had 50% error. So we were looking at the wrong point all the time. So a month and a half, I was taking measurements. I was looking at frequency that corresponded to 0.1 Tesla, but I should have looked elsewhere. I already had the signal, but it was elsewhere. So the signal was there, I was looking there, and I was thinking, why don't I see the signal? Anyways, that gave me a lesson, It's good to doubt yourself, it's good to doubt what you did. It's sometimes also good to doubt to others, right? So not to be skeptical of yourself only, but to be skeptical of others too. That's an important thing. All right, then there are carbino discs, which are very similar to hole probes, which I do not really like. You must have guessed that. But I like the geometry of carbino discs better because it's like a coil, right? There is magnetic field that comes from the center, and the current is generated in around the sphere. Physicists really like symmetry. That's one thing that we really like. I like spherical or cylindrical or circular symmetry a lot. And so if the current loops around the circle, I find it more appealing to me, more internalized. And so these are all classical magnetometers that measure. These measure static magnetic fields. This measures oscillating magnetic fields. But the magnetometer that I really like is an optical magnetometer, and I'll talk more about it in a second. This setup is in Berkeley at this point, where I did my postdoc, and my advisor there was very generous when he donated this to me. So I couldn't bring it with me physically. I could put it on my bag and carry it here, but it will soon be shipped here, so we will have hopefully a setup here to start things with, and then this is a huge help. It's like a startup gift, right? A great gift from a mentor. So I'll build one more of these, slightly different maybe, but the most important thing about this magnetometer is that you might have seen. So this looks like a big. What does it look like to you? It looks like a cannon to me, right? It looks like something that will be but it's not a cannon, it's a shield that is around it. It's magnetically shielding what's inside from outer magnetic fields. And the shield itself is the most expensive part of the setup. You wouldn't guess lasers are less expensive than the shield. So this is a very contained and beautiful setup. Besides, so this is an optical table. This is a table, basically, that has openings on it. That's what an optical table is. It has holes on it that are threaded. So you can turn and put things in and secure things in, right? A threaded hole accepts, I forgot how to call this in Turkish or in English. You turn vida, right? You turn something in. That's what a threaded hole is. You put a threaded. Anyways, I don't know its English. I've been back here almost a few months, and I've already forgot how to call it. By the way, what we call British key, English key, is a wrench in English, and it took me 3 years to learn it. I kept calling it. And they're like, bring me the English key. And then they kept saying, what does that mean? And they couldn't learn what I meant, and I couldn't learn wrench. Finally, I learned it. I also had a hard time with, in Turkish it means no, right? They kept saying, what do you mean? My advisor asked me, so did the setup work today? I said, so, I mean, what more can I say? Should I cry? No. So I said, and he was saying, so what does that mean? We worked for 7 years, and I think towards the end, he understood what I meant. Anyways, good. So this setup is, so I was talking about optical table. They're expensive. The most important thing, or the most expensive thing about an optical table is that, so this table, if a bus passes, if a train passes, if I walk by, if I put something on it, this table vibrates a little bit. Optical setups are very sensitive. There is a mirror, there is a laser. If things move by a millimeter, disaster happens. You have to align things again, and it takes an hour to do that again, blah, blah, blah. The most important thing about an optical table is for it to have isolated legs. So the legs of an optical table, the legs underneath. So here it's just, here you see the leg is just a metal. The most beautiful legs are isolated with air, so they float from the ground, sort of, so to say. So if you move them, or if somebody passes, if a bus passes, they do not vibrate, they do not feel vibration. They're isolated from the ground ever so slightly. Still, it is, even if you slightly isolate it, it still helps with the signal. So that every vibration, every movement, even if you turn on a microwave around, things could be picked up. That's why we have a shield. That's why we're careful with the legs. And those are also expensive experimental parts. But anyway, so it is as big as the usual, desk that you have. And this setup is as big as this, maybe like a pig. Maybe it looks more like a pig than a cannonball, a metallic pig that measures magnetic field. So how does an optical magnetometer work? Real quick, sorry, I'm taking long, I guess. Optical magnetometer measures still measures the spin's response to magnetic field, but it senses the spin's motion, the spin's magnetic field with a light, using the light-matter interaction, right? We send some polarized light beam, a laser light beam, to a sample, to some gas atom in a vapor cell that senses the magnetic field. So the magnetic field is first sensed by the spin, and very quickly what happens is that you, maybe I should move as quick. Okay, so very slowly, the magnetic field B, and if there is an atomic magnetic moment, meaning a spin, mu, if they interact, there is a torque. Torque means flipping, right? A spin that flips, that changes direction, that it points. And this happens at gamma. Gamma is the gamma magnetic ratio, so the Larmor frequency. So this flip, or this flip rather, so this is in the rotating plane, this is in the left plane. This rotation and this flip happens at the Larmor frequency. This is radio frequency, this is Larmor frequency. So if I turn things at radio frequency, if the optical electric field, if I send a light beam, if the optical electric field due to light beam matches the radio frequency, I successfully measure the magnetization of the spin flipping. That is the idea. So this is another way of describing this. Maybe this is too detailed. If you guys want to talk more about this, we can talk. This is the atomic energy levels that are the spin levels that are moving with the light interaction. All right. So my last two slides. Good. Okay. So the highlights, or rather one exciting application of magnetometry is dark matter searches and other spooky things, but dark matter searches is the first exciting thing. Dark matter, what is it? So again, I am an animal physicist and atomic molecular optical physics, but the application of my PhD work is in astronomy or astrophysics. I'm not an astrophysicist, I'm not a particle physicist. The way that I describe this might be a bit simplistic compared to how an astrophysicist or a particle physicist would explain. But the thing is, the way that I understand it is this, that in the universe, astrophysicists throughout the years, ever since Hubble was made in the 60s, I think, and put out to travel through the universe, to send us pictures, we have suspected that something is happening with the universe, with the matter in the universe. There are some signatures, not one, but 2, 3, or more, that hint at the existence of an extra mass in the universe that is localized, right? So we suspect that in the universe, centered at either at the center of our galaxy, or at the center of Sun, or at the center of Earth. We are not sure. We suspect that mass of particle that does not interact with light that much, non-zero. There is no such thing as zero on the universe. In nature, that's another important thing. You cannot measure zero. It's impossible. The thing that you measure as zero has error bars. Every sensor, every device that says it measures zero has an error bar, and it actually measures zero within that error bar. If the error bar decreases, if the sensor becomes more sensitive, then a peak might appear, then a signal might appear, right? Every sensor is limited to a noise. And when someone says I measure 0, they mean I measure 0 with this error bar. It doesn't mean absolute 0. Okay? In that sense, it is difficult to say dark matter doesn't interact with light at all. We can't say it interacts 0. It interacts very little. And it doesn't interact with other forces all that much as well. But it might have some interaction. The biggest interaction that it has is with gravity. Okay? So it interacts with gravity a lot, so much that the cosmologists or astrophysicists suspect galaxies were formed around clumps of dark matter in the early universe. So dark matter provided a bed. You know, if you consider the universe a sheet, dark matter clumped the sheet, made a hole, sort of, right? And didn't interact with other things but themselves and gravity, made a hole, and then the matter started clumping around that hole. Right? So some cosmologists work on that idea, and so they think that there must be a particle, a clump of dark matter, and they mapped this. They map where the clumps might happen. So they suspect there is a clump when you have a telescope, right? When you have a telescope in a space shuttle, when you have a telescope, you look at a distant galaxy. So here is a galaxy right there. When you have a clump of extra mass, dark matter, between the galaxy and your sensor and your telescope, you start getting extra images of that galaxy. So there's one galaxy, but because the light bends due to this extra mass, you start seeing two of those galaxies around. And there are what we call this gravitational lensing. It's like a lens that bends the light. And this is from NASA. They have measured, you know, this is the same galaxy, 4 images of the same galaxy. They suspect that there is a clump of dark matter there, and the same images of this galaxy in red circle. They suspect there is a clump of dark matter there. So this is not to prove that there is dark matter, but to insinuate, to hint that there might be dark matter, and clumps there. This maps where, so using this and the cosmic microwave background, cosmologists map where the dark matter clumps might be. However, this doesn't tell you what the particle is. It just tells you that there is something. It doesn't tell you what it is. It's like being in a dark room and hearing some voices. You don't understand if that's an elephant or a hippopotamus or just me making elephant sounds. You don't know, right? So if you're in a dark room. That's the idea. That's the thing that dark matter searchers do. They do not search for where the dark matter is or how it's clumped. They search for the particle nature of it. What particle makes this thing, makes this clump, makes this noise, right? So we are trying to identify the particle from signatures, from its signatures. At CERN, for the last 20 years, they were trying to hunt a dark matter candidate called WIMPs. It would be great if it was found. It would explain the dark matter riddle very nicely. No signature has been found. They scanned the mass range very thoroughly. They couldn't find a signature. However, they're still hopeful. I think they're still looking at the WIMP in some other masses. But because the WIMPs were not found, the physics community started looking at other particles. And I like to joke, you know, there must be, what could dark matter be, right? What particle could it be? They opened this big black book of possible particles. Right, you open the book. A comes up, say, axions. Okay, let's start with axions. Which is not true. Axions are a great fit for it. They actually were invented. By invented, I mean they were hypothesized to exist. In the 60s, an axion is actually a word. So, what is axion? Axion is actually a word like a GIF in America, in the US. It's a cleaning product. So it cleans a problem in physics that is not dark matter. In quantum chromodynamics, the existence of axion solves a problem, cleans a problem, therefore they called it the part of axion, very creative. So it was created, it was first hypothesized then, and lately in the last 10 years, people realized, or 15 years, people realized, it could be a good candidate for dark matter too, and we started doing experiments for it. As I said, there are maybe 20-25 experiments globally that search for axion dark matter in different frequency ranges. The thing that differentiates axion from WIMPs, the particle that CERN searches for, is that axions have very small mass. WIMP has a large mass, it's like a proton in mass. Axions is even lighter than an electron. Because it's so light, it could be simplified as a classical field that oscillates as a background oscillation. You guys probably don't know, before LCD TVs, nice flat TVs, we had category 2 TVs that had a long back, and you put antennas to them, and then for internet, on TVs, you put antennas, and then more than often the TV went off, the antenna went off, and we heard background noise, right? You saw the snows, as we call them, cardinal. Right? And this is somehow similar to that. There is a background oscillation. That snow is not due to dark matter. Let me be very clear on that. But it is somehow like that, an idea that there is a background oscillation that happens at some frequency, and we're trying to search for that oscillation that happens at some frequency, at a certain frequency. Right? And the idea of this is that this is a Hamiltonian, sorry for the non-physicist here. The idea is that if there's an axion A, there is some light that is generated. So again, sorry for the non-physicist, this is a Feynman diagram. An axion creates a light, a gamma, a photon, right? And then you pick up this photon. So the idea is that we put our experiment, so this is the axion field, we put our experiment in the axion field, where the axion field might pass. And let me be clear, axion field, if it exists, should be passing through us, through anything, through the Earth. It's passing through me, through you. It's not affecting us if it exists. It shouldn't be affecting us, it's not affecting us. But if you have a very strong magnetometer, if you have a very sensitive magnetometer, you should be picking it up. You should be seeing some signal due to it, if you're at the right frequency. Right? It's like a radio, right? There's a radio background that is Bilkent, radio Bilkent, and you're trying to tune to that, tune to 96.6, I think. You're trying to tune to that, somehow like that. Good. So this is how a typical axion experiment works. So this is one of the experiments that I worked on, that we published work of. So this is, I also like this. So we made some. Sorry. Oh, sorry. Hold on. So let me stop this. This is very psychedelic, right? This guy. Sorry, I can't stop the psychedelic thing. But try to focus on the right one. So you see the fluid moves. So this is a magnet. The fluid moves with the magnet. I found it very spooky when we did it. So this is I think very beautiful. What we did. So this is actually a glue, right? A die-cast, if I remember correctly. Sort of like an epoxy that dries up, becomes a plastic, a very strong plastic in the end. And what we mixed it with, it's a mixture that dries up over time. What we mixed it with was some magnetic dust. And then we mixed it, and then we wanted to test if it was magnetic, and when you put the magnet nearby, it moves, and it's black, right? Because we don't celebrate Halloween here, but because Halloween is closed. So, yeah, I thought this is one of the spookiest things that I ever seen. So if you're still not convinced that magnetic fields are useful, are worthy of our energy, our time, I want you to remember speakers work because of magnets. So the reason that you're able to listen to music is because of magnets. do they work? There is a magnet, there is a coil, current is run based on the sound that you're listening. If you're listening to Yeni Türkü, or if you're listening to Metallica, according to your taste, the voltage changes over time, right, according to the sound. And that moves because there is a magnet that creates a magnetic field, and either this magnet repels or appeals, either this is repelled or appealed to the magnet, and the drum on the speaker moves, and that's how the sound is made. And also there are motors that use magnetic force, that you run a current through it. There's permanent magnets, you run a current through it. When you run current, there is magnetic field generated, and the static magnetic field due to permanent magnets moves this, and you have a rotating current, right? Still very exciting. Good, thank you for listening. This is my favorite cartoon. This is how a magnetic discussion is usually made with hands, and I couldn't stop using my hands as well. This is very common, and we like making fun of ourselves like this. So thank you for listening. Does anybody have any questions? Yes?
What actions being lighter has to do with the background oscillations?
Good question. So, if a particle is light, you can, or has a very low mass, and it exists a lot within a given. So, depending on the mass of a particle, you have a de Broglie wavelength associated with it. If axion, it doesn't only need to be light, it also has to be a lot within a Broglie wavelength. If an axion exists, and if it's the dark matter, there must be abundance of it. There must be a lot of it, right? A lot of axions within a given area. And if you sit down and calculate the density that the axion should have, and it's the de Broglie wavelength for a given mass, you realize that within a single de Broglie wavelength of the axion mass, you would have a lot of I keep calling de Broglie, I think it's common. You have a lot of axion particles, right? So if a particle is light and also abundant, then it should be it could be treated as a classical background oscillation. So that is the answer, okay? But if it's a single axion particle that is just no friends, just sitting here alone, it would just be a particle. But if you have a lot of them in a struct in a single area, then they would act like a background oscillation. So it's like a statistical thing, I think.
So we are assuming they're abundant.
Yes, yes. In the regimen, in the point that they're abundant.
But if they are not?
If they're not, then it's a particle. But then you wouldn't be able to measure it as well because your sensitivity wouldn't be good enough. So the way that these axion experiments work, the reason that they work, is that they assume the full dark matter density that we calculate from observations, from cosmological observations, is due to axion. Right, axion makes the whole of dark matter, and the density that we calculate is true just for axion, right? Just axion makes up the whole dark matter density. So if that is the case, then there should be a lot of axion right now in that group. But this is an exciting application, but not the only application again. But this is pretty exciting. But again, not the only application of magnetometers. Still. Good. Anybody else? Yes. Hi.
What do you plan on working on in here in Bilkent?
Thank you. Yes, so I will work on optical magnetometers, like this one here. And we are already using one of them, optical magnetometers, sorry, in a network of them. And we will have one of them here too, to search for dark matter in a network of magnetometers. So if a magnetometer sees a signal but the other doesn't, then you could illuminate it as a candidate. It has advantages over having just a single magnetometer. But the most exciting thing that I plan to do is optimizing these optical magnetometers and trying to make them smaller with still a good coherence time, it would be very exciting. So these work at room temperature. They do not require any helium. These are optical, right? So you just need laser light to go through a sample, a cell of gas vapor. The most exciting thing would be to miniaturize them. They're already miniaturized. There are miniature versions of this that are, thumb-sized. However, they do not have large coherence times yet. So that would be very exciting to do. And to measure MRI maybe with them in the long-term plan, that would be very exciting. Again, what I do is magnetometry that could have different applications. Although, so the reason that we do not show spins, or I do not like the bar magnet drawing of a magnet, is that there are no magnetic monopoles. We do not think there are magnetic monopoles, right? So in electric field, there is electron and a positron. There are negative and positive charges separate, that exist separately. In magnetic field, we suspect that doesn't happen. We do not think there are monopoles that have negative or positive magnetic charges. However, you could search for monopoles with a magnetometer. Many physicists do not think that they exist, but they could be searched for, right? So these are exciting directions that I'll take, but I guess for me personally, the most exciting thing is to build a very fine working magnetometer. And once you know techniques of AMO, of atomic physics, you can move to different directions. I can move to ultra-cold atoms, cool down the setup, do something else, move in another direction. Or do nitrogen vacancy magnetic sensing. So on top of diamonds, or in diamonds, naturally occurring, in diamonds you have carbon atoms that are aligned in a lattice, right? Sometimes naturally occurring, those carbon atoms are exchanged for a nitrogen, for a silicon. And then you have a nitrogen atom engulfed in a sea of carbon atoms, and within the band gap of this diamond, you have the energy levels of a nitrogen or a silicon. And you can reach that energy levels optically because a diamond passes light through it. You can reach those energy levels optically, and you can use that atom to measure magnetic field in a very small region too. So I might enter that field at one point, But first, I'll start with optical magnetometers and using them in a network of setup to measure dark matter and optimizing them. I'm really interested in trying different shielding mechanisms, actually. Sometimes in experimental physics, people do tried and done methods, and they rely on, as we do in life, you learn one thing, everybody does it that way, and you think, okay, that's the only way to do it, right? You do not question, because life moves fast, and we only have finite energy. We are, as humans, programmed to live in a society, right? Well, not programmed, but we are used to living in a. The reason that we are the dominant species on the Earth is our inherent capability of collaborating, right? That's what Harari says in his book, right? We collaborate, we gossip. He says in what's his book? Deus Homo? No. Homo Deus? Homo sapiens. That's more true. In Homo sapiens, what he says is that we gossip, right? We gossip, we believe in each other, and then we try as a community. That's the idea. And in experimental physics, much like other communities, we think, okay, they do shielding that way. This must be the truth. This must be the only way. But there might be other ways, and there's no harm in trying. Although in academia, if you don't publish too often, you're deemed unsuccessful, and many people tend to find themselves tending to pick up the lowest hanging fruit, as they call it. Many people try to, as I do sometimes too. I'm not blaming others, but it's very common to do easy experiments, to do measurements that are easy to do, not to take risks with your work. But sometimes it is worthy, and sometimes the real progress is made when you take even so slightly a little risk with your time. Take some time to explore something that has been being used, has been unusual by others. But so yeah, I'm excited to try that out too. I'm just starting my lab out. Hopefully this semester. I'm very excited. I have received some funding too because I came to Turkey, so that's also very exciting. And yeah, so being an experimental physicist is very exciting. And if any of you, if they're undergrads who are in engineering or in physics, in chemistry, I would be delighted if you wanted to become an experimental physicist. So welcome to you to the dark side. No, it's not the dark side. It's actually quite fun, and if you're excited about doing things with your hands, if you like cooking, if you like gardening, right? If you like soldering, if you are interested when you're cooking, if you're also interested, not only interested in what you cook, or how, if you're also interested in how you cook it, right? If you find yourself thinking, what is the boiling point? Should I add salt to this? If you're on the highway, you're driving, you're thinking, I should slow down, there's some force that is pulling me apart. If you find yourself in situations that you visualize, that you see something happening and then you visualize, what is the force acting here? What might be happening here? If you're finding yourself looking at something and seeing forces come out of it, it might be good if you try, I'm not saying in a crazy format, but for visualizing. It might be good to try experimental physics. It's a very exciting and very satisfying field. In the end, it's slightly unlike engineering. In engineering, you learn about how to build something and you build it, which is good, right? You build it, it works, you feel happy. In physics, in experimental physics, you build something that is not built before. It might have been built in some format, but you change it, you change something about it. You enter the unknown, as he said. So you enter the unknown, and then when you're in the unknown, if what you built works, it gives you better satisfaction than in engineering. And I should say that he didn't mention, maybe he didn't know, I did my undergrad in electrical engineering, did a minor in physics, and in PhD I moved to physics. I sort of ran away from electrical engineering. I still value what I learned in undergrad in electrical engineering. It is very useful to know electronics, electricity in experimental physics. However, it's a different way of thinking. Right? You look at things differently than how an engineer does. But anyways, good. Any other questions? Did I answer the question? Sorry, I took too much time, I guess, with the presentation. Yes, hi.
Thank you for the talk, and you have shown a Feynman diagram of an axion decaying into a photon and
yes.
something else. First of all, what's that? And they say axion doesn't interact with light.
Ah, yes.
So, how does that work? What's the interaction there?
It's actually two photons. We crossed out one of the photons for any reason that I forgot. It's actually two axions forming into two photons. That's why it conserves energy, I guess. What was the second question?
what is the interaction
The
that
light.
allows this?
As I said, it's non-zero, right? It can never be zero. What people mean, the reason that they called it dark matter was that it didn't show up as a field in the telescope measurement. Looking at a telescope, you don't see a cloud. You just, you do not see this without. This is just a picture. In this picture, we put the dark matter, right? The dark matter cloud. We do not measure the dark matter cloud. We do not observe with light the dark matter cloud, but we infer it. And it interacts with light in what we call a Primakov effect, where it turns out two axions in the presence of a large magnetic field turn into light particles, photons. Right? So it is not the usual interaction with light. Our usual interaction with light is that light impinges on us and then reflects back, and then we see things. This is not what happens with MSO. However, it's still some interaction with light, I guess, that has light in it. So, I do not like making statements that say this doesn't happen at all. This has to be this way. You have to be. Nothing can be zero. If I might be corrected, someone might correct me, but based on what I have learned, and being an experimentalist, it's impossible to measure zero, and I do not think that. In equations you have zeros, yes, but then you can't measure them, and that's why you can't say for sure that monopoles don't exist. In the Feynman equation, there is a zero that says monopoles shouldn't exist. But we cannot prove it, right? Because we can't measure the zero. We measure zero up to a certain percentage, but then you have to keep measuring with higher sensitivity to prove that it doesn't exist, or you find something and it turns out it exists. So it opens up a problem, and that's why searching for dark matter is easier than the alternative, the modified gravity. I didn't even mention that. There are people who think yes, could exist, could be the explanation to what we observe, that gravity could work differently at higher speeds, at the speed of light, where gravity works differently, they say. I don't know, I have nothing against it, but it's difficult to prove. It's difficult to experimentally prove or disprove. So we have to do what we think scientifically is possible to do. All right, good.